Lasing condition. To get lasing, this condition has to be satisfied. Your small signal gain must exceed linear loss, right? This is CW laser theory. G0 has to be larger than L. If this is violated, not to mention Morlock lasers, you have no CW lasers. 根本就不会发光。好，所以这没有问题。But let's check the figure. This is the F curve, okay? Horizontal is the A0, the steady state solution amplitude of the second hyperbolic function. Vertical axis is F function. So F function is L minus G according to the previous page. So you got the curve like this. Okay? And if you still remember, the meaning of F function is net loss seen by the pulse wings. So that means this is the saturated gain. L is a constant always here. And L minus G equals F. So this must be the saturated gain G. 对不对？ L 固定在这里。 减掉 G 就会等于 F 啊 ，L 不动，我的 A0 改变，我的 gain 会改变，那减出来的高度不一样，我就打点，就画出这个蓝色的 curve 啊 ，F curve is this one. But what does the horizontal axis mean? What is the meaning when A0 is larger and larger? I purposely use these 3 examples to show you. When A0 is larger, of course, you got stronger peak power, but meanwhile, you have shorter pulse duration. 所以大致上是从没有 steady state pulse 开始有胖而矮的 pulse， 到越来越窄而高的 pulse。好，当你往右边走的时候，对应的 solution 大概就是这个样子。Okay, and when your peak power is bigger, your gain saturation is stronger. So this is smaller and smaller, so your F curve is monotonically increasing function. Okay. How about this point? 0. 0 means A0 equals 0. So it means no lasing, noise only. When A0 is non-zero, you have some pulse. No matter it's broad or short, it has some pulse. But when A0 itself is 0, 就是连振幅都是0，就代表我这里讨论的是什么？根本没有 lasing， 这个是只有 noise 存在的状况。And at this position, your gain is maximum. What is the corresponding gain? Your small signal gain, G0, right? Okay, so the distance means small signal gain. Okay, then if you check the F curve here, okay, and focus on the spatial point when horizontal axis 0, you got L minus G0. L is here, G0 is here, and it must be negative. Okay, because G0 has to be larger than L. Then L minus G0 must be negative. So this position here must be a negative number. 0 is here, so it's below 0. So overall speaking, if you want this passive Morlock laser get lasing, the requirement is the initial position of the F curve has to be negative. If this point is positive, no way, you cannot get lasing. Not to mention Morlocking. Okay, that's the point. Any question? Then, graphical solution. When the pump is adequate, That means your small signal gain G0 is not too big, not too small. Then the requirement H equals F can result in two crossing points or two solutions. Okay, just like this figure. The blue one is the F curve. The H one is the red one is the H curve. Remember, H curve is about loss saturation. F curve is about gain saturation. If your G0 is adequate, small signal gain is adequate. And the small signal gain depends on your pump. It also means pump is adequate. Then these two curves can have two crossing points. Each one represents one steady state solution. Okay? However, only the weaker solution is a stable solution against noise. So highlight here. This solution, it corresponds to smaller A0, a weaker pulse of broader pulse duration. This is stable. Another solution, although this is another solution, but it's unstable against the noise. The meaning is, if you send a pulse exactly equal to this condition, the pulse can repeat itself for every one round trip. But whenever there is a noise, after a few round trips, the pulse will be seriously distorted. It can no longer stay there. But for this stable solution, in the presence of noise, the pulse can maintain its shape. Noise cannot get amplified. So this is a stable solution. So experimentally, you can only observe this stable solution. Although the other solution is mathematically true, but you cannot observe it experimentally. Any question? 那你一定会觉得很奇怪啊，你怎么知道 weak pulse 是 stable, strong pulse 是 unstable? Is there any justification? Of course, you can justify it by numerical simulation. But is there any other way? We can justify this is true. You have to observe what's the difference around the stable solution point and the unstable solution point. What's the difference in this figure?
That loss is seen by the wings. So it's F.
Yeah, it's because I mentioned the concept a few slides before. 但是能从这个 curve 看出这件事吗？这张图看出这件事。为什么这一个焦点就没有那个问题啊？这个焦点就有问题？那就要看这两个焦点的附近两个 curve 的形状，两个 curve 的趋势有什么不同？ For example, here, if you move to the right, the red one is higher than the blue one. But for here, if you move to the right, the blue one is higher than the red one. And remember, this is about loss saturation. This is about gain saturation. So that means for here, if you try to increase your pulse peak or compress your pulse width, your loss saturation is stronger than the gain saturation, while here, the reverse, gain saturation is stronger than the loss saturation. That's the difference. And which one is more favorable in terms of compressing your pulse width, right? If you move to the right, it means you try to compress your pulse width. 那到底是哪一种是 favor？ 你可以借用我刚刚的这张图。 here. As I mentioned, when A0 increases, both curves go down, but with different speed. Okay? And the one case, it will lead to a narrower time window. In the other case, it will lead to a broader time window. Okay? And which is favorable in terms of post-compression? You need a narrower time window, right? 好，那两个 stable 跟 unstable solution，stable solution 的确会对应到 narrower time window to support your shorter pulse width. But for unstable solution, the reverse is true. When you try to compress the pulse, but you got the broader time window, which is unfavorable. Okay, that's one of the approaches to justify why one is stable or favorable, the other is unstable or unfavorable. Okay. So as I mentioned, this figure is quite useful. Okay, then practical problem. Overpump prohibits single pulse solution. Okay, if the pump is too strong, your small signal gain is too large, and as I mentioned, this distance means small signal gain. So when you crank up your pump power, your blue curve will be lower and lower because the initial position is lower and lower. It's good for lasing because, as I mentioned, this point has to be below 0. It has to be negative. A stronger small signal gain will give you more negative initial point, which is good for lasing. But the problem is when the blue curve is too low, there is no possibility the blue curve can intersect with the red curve. Okay, just like this case. Then there is no crossing point. There is no solution. So your pulse can, your laser can get lasing, but cannot get more locked. Okay. By observing this figure, it could be like that. But in practice, it does not mean you have no pulse at all. It simply means you have no single pulse solution. Single pulse solution means every round trip you have one pulse only. Okay? In this case, when the two curves have no intersection, it actually implies multiple pulses can exist per round trip. Okay? 所以焦点只是代表有 single pulse solution， 一个 round trip 只有一发 pulse。那出现这个情况呢，你做实验的时候其实也不会没有 pulse， 它还是有 pulse， 只是它一个 round trip 可能有2发 pulse， 或者有3发 pulse。But that will disturb your repetition rate, right? You have a 50 megahertz laser initially, but when you do so, if you measure your pulse trend by your scope, you will see even higher repetition rate occurs if your pumping condition is inadequate, it's too strong. You will see multiple pulsing. Okay. But again, how do you know multiple pulses actually exist? Could you justify? By, of course, not this curve, by other means. 为什么很强的 small signal gain， 很强的 pump， 这个图看不出来了，因为没有焦点嘛。为什么它就是代表 multiple pulsing？ Again, could you try to justify by this figure? This figure can tell you why there are multiple pulses per round trip. Okay, so think about if your pump power maintains, your average power maintains, and if your pulse is splitted into 2 pulses per round trip, what happens? What happens to these figures, to these curves? If your pump power maintains constant, your average power maintains constant, which curve will not change? Blue one or red one? As I mentioned, one is about loss saturation, the other is about gain saturation. Which one is unchanged? The red one is unchanged. Red one is about gain, right? Gain is fixed, as I mentioned. But when your pulse, single pulse, is split into 2, and the average power is the same, that means each of them contains only 50% of the energy. So your peak power reduced. Your blue curve will change, right? Your blue curve, if your peak, each pulse contains only 50% energy, your peak has to be reduced, and your blue curve will be shallower. Okay? So that means the distance is shorter, or h function is smaller. Okay? Then what happens? F function is maintained, unchanged. It's about gain. H function is lower. It's about loss. So you have the possibility of crossing point again, right? 好，所以你可能没办法直接从这个 curve 去思考出来为什么 multiple pulsing 可能存在，但是你用了刚刚那个 curve 就可以想出来。Question？
这个是假设说要降下来 ，H 降下来，那跟 F 有2个交点，那还是会回到最第一个 graphical solution 那个。
Sure， 对，会。
还是会有一个人。
然后你还是只能看到 stable solution， 没错。Even multiple pulsing, you can see stable solution. Stable multiple pulse solution still. Okay. And it's a very realistic situation. In my laboratory, we see the behavior before. When you got more locked, it's pretty present. But if you keep on increasing the pump power, you will lose single pulsing. It's hardly be observable from OSA, optical spectrum analyzer. It does not change. But if you measure the time domain characteristics by photodiode and oscilloscope trace, previously it's a very stable periodic pulse trend. Pump power too large, you will see some strange signal. Maybe double pulse. If you increase the power even stronger, pump power even stronger, you can see triple pulse, higher and higher. Okay. And usually it's not a coincidence. For example, double pulsing, the second pulse does not always occur at the middle between 2 adjacent pulses. So it's not a very pleasant situation, right? 如果它不是中间，那你就不会出现什么简单的重复率倍增，你会出现一些很奇怪的东西。它会出现在哪？其实你没办法预测，会乱跑。所以这是很常发生的事情。所以 stronger pump power is not always good for your Morlock lasers. You have to be careful. Okay, so maybe let's stop here. We can move on this Thursday.